This is everyday life scenario. People have different preferences, but also share common goals. They need to balance their own preferences with those of their partner.
Abwechseln. Wir machen jetzt jedes Jahr immer nur das, was du möchtest. Und jetzt will ich einmal, dass wir auch mal auf meine Idee eingehen. Und dann fängst du schon wieder an zu meckern, ja. Dankeschön.
Ich habe doch gar nicht gemeckert.
How we and other animals do this has been studied for a long time. In the classical game theory, one such example is called the Battle of the Sexes, or Bach-Stravinsky. In this hypothetical scenario, people with different preferences would like to spend the time together, so they need to decide whether to go to a Bach or a Stravinsky concert, or to a beach or mountain vacation. Such interactions between the two people are called dyadic interactions. Because we are such hypersocial species, we often interact in a very helpful, cooperative way, but we also can be highly competitive. The games studied in the classical game theory, such as Bach-Stravinsky, are quite abstract. They assume that the players don't see each other and act without any knowledge of the other's choices, or strictly one after another. In real social interactions, however, we often observe each other and make mutual decisions more or less simultaneously in real time. This also means that we can take facial expressions, gestures, and ongoing actions of others into account. To incorporate these aspects, we developed a novel setup called the Dyadic Interaction Platform, in which the two players can see each other and interact face to face. So their mutual actions and choices are transparent. Therefore, we refer to this approach as transparent games. Because our goal is to understand the evolutionary history of human interactions and to gain better insights into the underlying neuronal mechanisms, we designed our platform to be versatile so that it can be used not only with human subjects but also with monkeys. For example, we had two participants to play a game where initially each player had different individually preferred option that gave the larger reward. For instance, player 1 would prefer red and player 2 blue. The dyadic task, however, was designed in such a way that selecting together or coordinating on any of the two options was beneficial for both players. The coordination was always better than no coordination, but there was also inherent conflict of which of the two coordinated options to select, because one coordinated option favored one player and vice versa. Both species learned to coordinate, but in different ways. Human dyads alternated between the two options, taking turns to ensure equal, fair distribution of rewards. Macaque monkeys, on the other hand, converged to simpler, static strategies. For instance, one monkey would selfishly and consistently lead to his own preferred option, and the other monkey would follow.
So in our group, we're interested in looking at whom children are attending to in their environment and how they choose which objects to look at in their environment and whom they're learning from. This may sound a little bit different from what Igor and his colleagues are doing, but it's actually the same context of embedding learning in the social interaction that children are typically faced with and looking at how learning is influenced by whom children are interacting with in any social context. So when we saw the possibilities that the Dyadic Interaction Platform allowed us, we realized that this was a game changer for research on language and cognitive development in young children. That's because it allows us to look at how children are learning in these natural social interactions where they can see who they're interacting with, while at the same time we can control what we're presenting children during the learning interaction. So we decided to build our own version that's more suitable to work with children, and we call this version the DIPSy. What we're currently doing is looking at the extent to which children learn new words for objects faster when they can see that either their caregiver or their best friend is really interested in knowing the label of a particular object. This allows us to look at the extent to which social curiosity plays a role in boosting learning in young children.
We do not base our decisions solely on hard facts and potential monetary outcomes. When we interact with others, emotions play an important role. This contrasts with classical game theory, which often assumes that players act rationally and independently, without direct social interaction. It makes a difference whether we see our partner, whether we know each other, whether we like each other, or simply whether they smile at us or look angry. Body language and facial expressions play a fundamental role in social interactions, as they convey crucial information about intentions and emotions. In our lab, we don't only study how motivations and emotions impact our behavior and cognition. We also explore how we keep our emotions under control. Take the classic poker face, for example. There's a good reason why keeping a straight face is so important in a game where your opponents are watching you. Not giving away your intentions can be a huge advantage, but that is easier said than done. So how do we manage it, and what's actually happening in the brain? To answer these questions, the Dyadic Interaction Platform is an incredibly powerful tool that lets players interact while displaying a full range of naturally occurring emotional expressions. With our setup, we don't just observe how players behave and make decisions. We can also measure subtle muscle activity in the face to better assess their emotional states. And to uncover what's happening in the brain, we record brain activity directly from the surface of the skull, giving us a deeper look into the neural mechanisms underlying joint decision-making in social interactions. The EEG measures brain activity in real time, allowing us to estimate the level of activity in specific areas during different tasks. But what makes the Dyadic Interaction Platform particularly fascinating is something called hyperscanning, the simultaneous recording of the brain activity from both participants. This gives us a readout not only of how the brain guides our own behavior, but also how it processes and responds to our partner's behavior.
What we have seen in recent years, that our new approach not only allows us to study macaque and human interactions in a much more realistic way, it also enables us bridging to different disciplines. For instance, close collaboration with psychology groups, such as ANNES or NIVES, creates exciting new opportunities. For example, to study behavioral neural mechanisms of social learning in the interactions between the parents and the children.